Hello, my dear student. Welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to discuss about the module titled Capillary Electrophoresis, laser-induced fluorescence detection, known as CE-LIF, under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to know the history of capillary electrophoresis. You will also know the capillary electrophoresis and its characteristics properties. You will learn the concept of electroosmotic flow and mode of capillary electrophoresis. You will also know the instrument of CE-LIF and the detection technique of CE and why we use laser in fluorescence as a detector. In little over 2 decades, capillary electrophoresis, known as CE, has emerged as a powerful analytical technique for determining the chemical composition of mass limited sample. It enables rapid separation with high separation efficiency, compatibility with a small sample volume. C has been used for variety of application, including determining of inorganic ions, environmental, food, clinical analysis, peptides, protein separation, single cell assay, and DNA sequencing. The state of the art of CE is addressed in several recent reviews. The diminutive capillaries implied in CE, the associated small volume, and temporarily narrow peaks, which results from the high efficiency separation, complicate detection. Detection in CE is most commonly performed on column by use of absorbance, often diode array, and detection. To achieve better performance, a variety of other detection methods has been developed for CE, including conductivity, radiochemistry, refractometry, and electrochemistry. Coupling CE to nuclear magnetic resonance and mass spectrometer enables identification of unknown compounds after a separation by providing an information-rich detection scheme for structural determination. Although laser-induced fluorescence, known as LIF, suitable for analysis of large variety of analytes, result in a highest sensitivity in CE. Little structural information can be obtained from single wavelength fluorescence detection. Wavelength resolved fluorescence detection is a mean of maintaining low limit of detection while furnishing valuable spectroscopic information about fluorescent species. This makes it an attractive mode of detection for trace analysis in CE. The development of capillary electrophoresis. Electrophoresis has been defined as the differential movement of charged species, ions, by attraction or repulsion in an electric field. Electrophoresis as a separation technique was introduced by Tiselium in 1937. Placing protein mixtures between buffer solution in a tube and applying an electric field, he found that sample components migrates in a direction and at a rate determined by their charge and mobility. For his work in separation science, Tiselium was awarded Nobel Prize. Separation efficiency in free solution as performed by Tiselium was limited by thermal diffusion and convection. For this reason, electrophoresis traditionally has been performed in anti-convective media such as polyacrylamide or agarose gel. Gel in the slab or tube format have been used primarily for the size-dependent separation of biological macromolecules such as nucleic acid and protein. Although it is one of the most widely used separation technique, slab gel electrophoresis generally suffers from long analysis time, low efficiencies, and difficulties in detection and automation. An alternative to the slab format is to perform the electrophoretic separation in narrow bore tube or capillary. Since narrow capillaries are themselves anti-convective, gel media are not essential to perform that function. This allows the performance of free solution or open tube electrophoresis as well as the use of traditional Z medium in capillary. Initial work in open tube electrophoresis was described by Hodgson in 1967. At that time, since only millimeter bore capillaries were available, Hodgson rotated them along their longitudinal axis to minimize the effect of convection. Later, Whitman and then Mickers performed electrophoresis in approximately 200 micrometer internal diameter capillaries made from glass and Teflon respectively. In this early 1980s, Jorgensen and Lucas advanced the technique by using 75 micrometer inner diameter fused silica capillaries. Jorgensen also clarified the theory, described the relationship between operational parameters and separation quality, and demonstrated the potential of high-performance capillary electrophoresis as an analytical technique. The capillary electrophoresis. Electrophoresis is a separation technique based on different mobilities of charged molecule in a conductive medium, usually aqueous solution under an applied voltage. Capillary electrophoresis, known as CE, is a modern high-performance separation method. The separation is based on different migration of analytes in a capillary over which a high voltage, typically 10 to 30 kilovolt, is applied. Typical inner diameter of commonly used capillary are in the range of 25 to 75 micrometer, and the detection is usually on column. Let us discuss the electro-osmotic flow. A fundamental constituent of operation is electro-osmotic, electro-endoosmotic flow, which is EQF. This electro-endoosmotic EQF is the bulk flow of liquid in the capillary and is a consequence of the surface charge on the interior capillary wall. The EOF results from the effect of applied electric field on the solution double layer at the wall, which is seen in the figure. The EOF controls the amount of time solutes remain in the capillary by superposition of flow on the solute mobility. This can have the effect of altering the required capillary length but does not affect selectivity. The basic instrument setup of CE is shown in figure. A capillary is filled with electrolyte and both ends are immersed in buffer reservoirs. A high voltage power supply applied the electrophoretic field with the electrodes between two buffer reservoirs. The sample solution is injected from one end of the capillary, that is called inlet end, and on line detection is generally placed near the outlet end. Absorbance in UV visible region is the most common form of online detection. Other detection techniques are fluorescence, amperometry, conductivity, potentiometry, mass spectrometry, etc. Currently, available commercial CE systems are equipped with capillary temperature control function and an auto sampler in order to improve the reproducibility. The movement of analytes. Separation by electrophoresis is based on differences in solute velocity in an electric field. The velocity of an ion can be given by V is equal to mu E, where V is the ion velocity, mu E is the electrophoretic mobility, and E is the applied electric field. Electrically charged particles are moving in the applied electric field in a direction determined by its charge and the field orientation. Positively charged particles are moving towards the negative pole and negatively charged particles are moving towards the positive pole. A charged particle is characterized by an electrophoretic mobility mu, which is defined as mu is equal to V by E or V into L by U m square by Vs, where E is the intensity of the electric field, U is the applied voltage, L is the total distance between the electrodes, the total length of the separation capillary. The characteristics of capillary electrophoresis. There are several characteristics of CE which are following. Electrophoresis is performed in narrow bore 25 to 75 micrometer internal diameter fused silica capillary. High resistance of the capillary limits current generation and internal heating. High voltage, which is 10 to 30 kilovolt, and high electric field, which is 100 to 500 volt per centimeter, are applied across the capillary. Detection performed on capillary, no external detection cell is required. A small sample volume. only 1 to 10 nanoliter injection is required. High efficiency, N is greater than 105, and short analysis time. Numerous mode to vary selectivity and wide application range. Simple method has been developed. Operates in aqueous medium and automated instrumentation. So these are the characteristics of CE. Now let us talk of modes of CE, which is mode of capillary electrophoretic. Different modes of capillary electrophoretic separations can be performed using a standard CE instrument. The origin of the different mode of separation may be attributed to the fact that capillary electrophoresis has developed from a combination of many electrophoresis and chromatographic techniques. In general term, it can be considered as the electrophoretic separation of a number of substances inside of a narrow tube. Each, through most applications, have been performed using liquid as the separation media. Capillary electrophoretic technique encompasses separation in which the capillary contains electrophoretic gel, chromatographic packing or coating. The distinct capillary electroseparation methods include capillary zone electrophoresis, which is known as CZE, capillary jet electrophoresis, which is known as CGE, micellar electrokinetic capillary chromatography, which is known as MEKC or MECC, capillary electrochromatography, which is known as CEC, capillary isoelectric focusing, which is known as CIEF, capillary isotachophoresis, CITF. In electrophoresis, a mixture of different substances in solution is introduced, usually as a relatively narrow zone, into the separating system and introduced to move under the influence of an applied potential. Due to differences in effective mobility and hence migration velocity of different substances under an electric field, the mixture then separates into a spatially discrete zone of individual substances after a certain time. I want to explain the table. In this table, we are going to discuss all the modes, their separation mechanism and application. Let us start with the first one, which is capillary zone electrophoresis, known as CZE. The separation mechanism for this CZE is based on the mobility differences of analytes in an electric field. These differences are dependent on the size and the charge to mass ratio of the analyte ion. This can be used for charged molecule in separation of charged molecule. Let us talk the second one, which is known as capillary gel electrophoresis, CGE. The separation mechanism for CGE is based on the solute size as the capillary is filled with a gel or polymer network that inhibits the passage of larger molecule. This can be used for separation of macromolecule such as protein and DNA. The third one is micellar electrokinetic chromatography, which is known as MEKC, and the separation mechanism is based on the differential partition of the solutes between hydrophobic interior of the charged micelles and the aqueous phase. This can be used and their application in the neutral and charged molecule, separating the neutral and charged molecule. Let us talk about capillary electrochromatography (CEC). Capillary is packed with a stationary phase that can be capable of retaining solute in a manner similar to the column chromatography, and this can also be used for neutral and charged molecules. The capillary isoelectric focusing CIEF. This the separation mechanism is based on the analytes are separated on the basis of their isoelectric points, jitter ionic applications, and finally the capillary isotachophoresis CITP. The separation mechanism for this is the sample zone migrate between a leading electrolyte at the front and trailing the electrolyte at the end. All of the solutes travel at the same velocity through the capillary but are separated on the basis of differences in their mobility. Protein and peptides, anions or cations, are separated using this technique. So this is all about mode of CE. Detection of CE will be discussed in this slide. The most common mode of detection in CE is on-capillary detection. In CE, migration velocity of each solute through the capillary is a function of its electrophoretic mobility in conjunction with the electro-osmotic flow EOF. Since detection occurs on capillary, these forces are operative as the solute is transferring the detection window. As a result, slower moving components spend more time migrating past the detector window than their more rapid moving counterparts. Currently, there are many detection techniques which are available for the CE detection, such as absorbance detection, fluorescence detection, electrochemical detection, conductivity, and mass spectrometry, etc. In this, UV visible absorbance detection and fluorescence detection were discussed. Let us discuss the fluorescence detection. The most widely used CE detector is based on fluorescence, using either an arc lamp or a laser as an excitation source. This highly sensitive and selective detector is especially important in biological applications. Fluorescence is expected in molecule moles. The fluorescence detector with lamp-based incoherent light source are of low cost and good commercial availability, but further improved on detection sensitivity is limited by low excitation power intensity and considerable light scattering from the capillary wall. In 1985, Gassman et al. Reported the first application of laser-induced fluorescence detection in CE. LIF produces remarkable improvement on detection sensitivity because of monochromaticity and coherent nature of laser light. At present, LIF is the best detection scheme in CE as far as sensitivity is concerned. The main advantage of fluorescence detection compared to alternative detection technique based on absorption measurements such as UV visible lies in a greater sensitivity. This greater sensitivity results from the fact that background emission due to the buffered solution is very low by comparison with the emission from the fluorophores. In another word, signal to noise ratio is not a function of detection cell path length. For those fluorescent molecules, fluorescence detection provides selective excitation of the analytes to avoid interference. Fluorescence is an important CE detection scheme mainly because it adds in analyte specificity and can provide extremely low detection limit. Detection limit ranges from approximately 10 to 15 to 30 to 10 to 20. Indirect fluorescence detection is typically less sensitive than direct fluorescence detection. However, it is usually more sensitive than direct UV detection. Another main disadvantage of indirect detection is that its universal nature could become a hindrance with extremely complex sample which may contain interfering species. Let us discuss CE-LIF instrumentation. The instrumentation is equipped with DPSS Nd:YAG laser, diode pumped solid state neodymium doped yttrium aluminum garnet 1064 nanometer with a frequency doubler emitting light with a wavelength of 532 nanometer. The laser beam is focused with a quartz lens with a focal length of 10 millimeter into the center of the capillary held in the adjustable clamp positioned on micrometric XY stage. Fluorescent radiation is collected with a microscope objective and directed through an optical slit, special light filtration, towards a photomultiplier tube (PMT). Two filters are inserted in front of the PMT to ensure optical filtration. The entire optical setup is covered with a light protection cover, sealed. The carousel with injection and background electrolyte BGE vials and the high voltage electrodes is placed in the protective plastic cover equipped with a safety switch, which turns off the HV if the protective cover is removed by protected operators from electrical shock. So student, let us now summarize what we have learned in this module. CE displays an enormous efficiency and possesses inherent advantage over conventional separation techniques. Fluorescence detection for CE commonly employed laser as an excitation source. Laser emit intense radiation with extremely narrow bandwidth, high spatial coherence, and negligible chromatic aberration. Their output is easily focused on the small flow channel of the capillary. The detection of several hundred molecules in CE employing laser-induced fluorescence are the ultimate goal of detecting a single molecule with probably be attempted in the near future. So this technique will going to give us a very nice separation as well as detection technique in future. Thank you very much.